Hi, I'm Zor. Welcome to Unizor Education. I would like to continue something which I have actually been talking about during the last couple of lectures. It's the behavior rotation primarily in the central field. Today we will consider two problems. One is trivial and it basically follows exactly from the formula which we have derived in the previous lecture. And another is a little bit more complicated as far as the calculations are concerned. But don't worry, everything is fine. Now, this lecture is part of the course called Physics Plus for All, presented on unizor.com. I do suggest you to watch this lecture from the website, even if you found it, let's say, on YouTube or somewhere else. Go to the website, because the website contains both lecture, which is video presentation, and the notes for this lecture, which basically like a textbook. So it's much more beneficial. Plus, whatever you do on the website is well positioned, like one after another in a logical sequence, all these lectures. So if you go by logical sequence, you will know what you are doing basically, and you will not have a problem. Right now I'm referring to the problem to some problems which I have solved in the previous lecture, so you have to really preserve this logical sequence. Okay, now let's go. So the first problem is you have let's say you have a plane, frictionless, and there is a object of mass m rotating on a radius r. So we have mass and we have radius and we have angular speed. So my question is, well, obviously there is a force which keeps it on the orbit, because if there is no force between the center of this circle and the object of mass m, it will just fly away along the along some trajectory, tangential trajectory, a straight line basically. So this force is, as we know, centripetal force. So it's a vector. Now it's obviously a central force because it's always directed towards the center. So it's a vector, and obviously it has coordinates fx and fy. So what I would like to do is I would like to know these coordinates basically. What is fx and fy? Okay. What do we know about this force? It's a central force, which means central force should be vector f should be parallel to position vector r. All right, position vector r is basically x of t and y of t. That's coordinates of this point in some Cartesian coordinates on this plane. Okay, so we know that. Okay, so let's try to use this, and what we can say is the following. We know what x of t and y of t is. It's a uniform rotation, which means x of t is equal to radius r cosine omega t. Omega is angular speed, so omega times t is angle of rotation by the time t, and cosine of this angle would be my x coordinate. Well, assuming that at time t the x coordinate is r and y coordinate is 0. So y of t would be equal to r sine of omega t. Now, how can we find the force if we know how the object is moving? Well, very simply. You have the second law of Newton, right? So f vector of t is equal to mass times acceleration of t, right? Now, what is acceleration as a vector? It's a derivative of velocity. What is velocity? Derivative of position. So let's just have these two derivatives. x b. Now this is velocity now. So this is position, this is velocity, this is r of t, this is v of t, and this is a of t, acceleration. That would be the second derivative. Okay, first derivative. Derivative of cosine is minus sine, and internal function is omega t, so another omega would be outside. So it would be minus omega r sine of omega t. Now, derivative of sine is a cosine, and times omega, so that would be omega r cosine omega t. Okay, second derivative. Derivative of this, again, from sine is a cosine with a plus, so that would be, and another omega, so it would be minus omega square r cosine omega t. And this would be, from cosine is a minus sine, so again, and another omega, so it's omega square r sine omega t. Now here, very important, you see, this is vector acceleration. It's collinear with the position vector. You see, r cosine, r sin, I sine, r cosine, r sine, and the only proportionality is minus omega square. So, if we will multiply it by mass, we will have that the f of t is equal to minus m omega square position vector. Right? Mass times acceleration minus omega square, and r cosine and r sine are exactly the same as these ones. So this is basically what we need. So fx equals to this times cosine of omega t, and this is this coefficient times sine of omega t. So again, I think I forgot r. I'm sorry, r. Should be r as well. R. And then r of t. This r. Omega square r. No. Again. If I put r here, there is no need for this. But if I will put it as coordinates, minus m omega square r cosine omega t, and fy t is equal to minus m omega square r sine omega t. So that would be, that's where r is. There is no r because r is inside vector r, position vector. Okay, so we have found this, and what's the magnitude of force? Magnitude is equal to this square plus this square and square root of this. Obviously cosine and sine square and square will be given 1, so that will disappear, and the magnitude will be m r omega square. Only this piece. Minus obviously will disappear when we square it. So that's our magnitude. Okay, basically that's it. We found the expression in coordinates and the magnitude of this vector. And direction is, you see this minus, in this minus, it's opposite to position vector. So position vector goes from the center towards the position, and the centripetal force goes backwards. And there is a coefficient between them, which is minus m omega square. Okay, now, the second problem. Okay, the second problem is a little bit trickier. multiple square. Okay, so here is another problem. Let's consider that there is a hole in this plane, and the plane is perpendicular to the force of gravity. So it's horizontal plane, and the thread which holds this particular mass goes through this hole down, and I hold this with my hand, let's say. So I hold this thread with the left hand, and with the right hand I'll just launch the rotation, and it will rotate, mass m, radius r. Obviously the force, which is the tension basically of this thread, is supposed to be equal to the magnitude of the centripetal force, which holds on the orbit. Okay, now my question is, what if instead of a hand I will put some kind of a weight, mass m0, and obviously the force with the force of gravity, m0 g, but g is acceleration of gravity. What will be m0? Well, this is the simplest question, because obviously this force of gravity should be equal to the magnitude of the centripetal force. It's central because it goes through the center. There is no additional rotational force. The force is only through the center. So there is no doubts that it's supposed to be equal to tension of the thread, and obviously m0g should be equal to mr omega square, from which mass is equal to this. So that's the answer. Now, more complicated answer is the following. What if instead of m0 we will add something else, plus m1? Now, this force will pull down stronger, obviously, and the thread should be, shorter. The radius should be shorter, and at that point it will stop shortening. Whenever the acceleration of this thing would be sufficient to neutralize additional force, the orbit will be on a shorter radius, but it will be fixed at some point. So my question is, on this new point, what will be nu r nu and angular speed omega nu? I would like to determine what are they. Well, the first answer actually is quite obvious, because again, a new force, which is m r nu and omega square nu, should be equal to the force of gravity whenever I combine these two masses together. So this is one equation. But we have two independent variables, radius and angular speed. So we need the second equation to do this. Okay, but here we have to recall the law of angular momentum conservation. Why it's applicable here? Well, for a very simple reason. The force is still central. So we have not changed the rotational component. We just change the central force, which pulls towards the center in this particular case, which means that whatever the angular momentum was before should be retained. Okay, so what was angular momentum before? L is equal to r times vector product with a p. Well, p is obviously mv. Mass is not a vector. So that's basically m times r vector product b. That's what it was. Okay. Now, consider speed vector of speed and vector of position. Now, whenever we have a stable circular orbit, speed is tangential and radius is perpendicular to this. So they are perpendicular to each other, which means that the sine of angle between them is equal to 1, and the modulo of this is actually mass times r times v. Their lengths, multiplication of their lengths, because the vector product it's a vector whose length is length of one, length another, and sine of angle between them. Okay, so from which we can actually find out what have we found out? Modulo of vector r is r. Modulo of vector v. Now, do you remember that v is a first derivative of r, right? So if r is r cosine omega t and r sine omega t, then the first derivative is minus omega r sine omega t, comma r omega cosine omega t. So there, the magnitude of this vector, this is v. The magnitude is square of this plus square of this, which is basically r omega, right? R omega. So the magnitude of v is r omega. So the whole thing is equal to m r square omega. And that is supposed to retain, which means it's supposed to be equal to m r nu square omega nu. This is my second equation. Well, from which mass obviously can be cancelled out, and what I have is the second equation, r square omega equals to r square nu omega nu. So I have a system of two equations with two unknowns, and all I have to do is just plain mass and solve it. Well, this is kind of plain algebra. I can't do very fancy about this, so I'll just express omega nu from the second equation, which is r square omega divided by r nu square. Substitute into this one, and I will get m r nu omega square, which is r to the fourth omega square divided by r nu to the fourth, equals to m0 plus m1 g. From which I get, this is, instead of this I will put the third degree here, right? So r nu cube is equal to, this goes here, this goes there. So it would be r to the 4 omega square divided by m plus m g. So that's my nu, which means my nu is equal to cubic root, and from this I find omega nu is equal to r squared divided omega divided by r squared nu is equal to r squared omega divided by, oh my god, that's kind of complicated, right? Divided by cubic root of r4 omega square and multiply by cubic root m0 plus m1 g. Well, kind of complicated formula. Nevertheless, whatever it is, and you are free to check if I'm right. Maybe I made a mistake. I was thinking about maybe find this problem or similar problem somewhere just to check myself. I didn't find it, but you can check it obviously. So that's basically it. That's all I wanted to present today. These two problems, one relatively simple, another a little bit more complicated. And I do suggest you right now to read the notes for this lecture, and that's where you can check my calculations. So you go to unizor.com, you choose the physics plus for all, and the part of this course is laws of Newton, and in that part you can find problem 5. So read it, and it's very useful actually to exercise this type of approach in education. You listen to the lecture, you watch the lecture, you read the textbook, which is exactly the same thing, and then what I do suggest you to do is try to repeat both solutions to both problems separately without looking at my notes and without watching the lecture again. Just do it yourself. You have the problem is presented in notes. Don't read the solution anymore, just do it yourself. Very useful. Okay, that's it for today. Thank you very much and good luck.